Our next presentation is automated test and retest utilizing AADL and SysML models by Shawn Kline. Shawn is a Chief Systems Engineer at Innovative Defense Technologies. He has over 20 years of systems engineering experience developing and working on advanced sensors, radar, control software, model-based systems engineering, and automated analysis of real-time systems. Here's Shawn.
Hello, I'm Shawn Kline with ATRT, and I'm here today virtually to talk about automated test and retest, ATRT. For ATRT, we are using a model for the basis of automated analysis from recorded test data from a system under test, or systems if interoperability testing is the focus. And we have an Army SIBR that we're working to do just that. The topic name is Model-Based Testing of Integrated Aviation Mission Systems. The intent of the topic is to test an implemented aviation platform using instrumented recorded data, and then test that data against the behaviors and requirements that are defined in an AADL model. And I've included some of the SIBR solicitation language directly in the title chart here. So we're doing that to ensure that the system passes the requirements and it's compliant with those requirements. The data, in this sense, can come from high fidelity simulations of the systems that you're designing, if you're sort of more on the left side of the classic engineering V chart. Data can come from virtualized systems running in digital ecosystems. It can come directly from the system integration, the SIL labs, or from hardware in the loop test events out in the field. The test tools should support the full life cycle from simulation to implementation. And then my final note for the title chart here is we are partnered with Carnegie Mellon SEI on this. We have been working with them closely. We will continue to work with them closely. We are in a phase 2 right now, and we hope to transition this to a phase 3 with our partner, Carnegie Mellon. A little bit of just agenda here. I'll give a little bit about our company, just one chart there, and then a little bit of background on ATRT. From a technology overview point of view, our roots are in SysML. We have a very mature technology that has been deployed for many DoD platforms, conducting post-test event analysis for things like mission readiness assessments or certification of events. And we actually have some versions of our tools that have been deployed directly on Navy surface ships to conduct near real-time analysis during an actual at-sea test event. And it's through the Army SIBR topic that I mentioned that we're trying to extend that capability into AADL. Our roots are in SysML. This was, the research topic to extend that into AADL. And I'll quickly get into a summary of the AADL to ATRT interface. From a demonstration point of view, we're not going to do any demonstrations on this presentation. We are looking for requests from folks to get together separately so that we'll allow time to dig in and show the models and the tools, the dashboards within ATRT. We have recorded data from a small UAV system that we're building for this project. During that demonstration, we'll load in the data, we'll process the data on these end-to-end test flows within the model, and then showcase the tailored objective quality evidence reports at the end. And then also cover what our accomplishments are to date in the project. A little bit more on our company here. We are a small company. We have grown through the SIBR process. We have multiple phase 3s that are active, that are being worked. You can see on the map here with the 5 red dots there. Those are the 5 major locations that we have at IDT, and those are really driven by customer interactions and platforms that we are currently working on test solutions for. From a core competency point of view, systems engineering, certainly including MBSE, automated testing, focusing on both automating the test conduct, what the operators are doing with the systems, as well as the back-end data analysis. And then we're also spending a lot of time on virtualizing systems and getting those up and running and deployable within digital ecosystems so you can connect them together to do multi-platform mission engineering threads and conduct interop testing. just to point out a couple of our sites, we have one up here in Massachusetts, Fall River. That one is tied to the submarine community. We have one in Mount Laurel, New Jersey. That one we are working directly with, big contracts with Aegis and directly with the Prime. That's also, in New Jersey as well, near that location. The Prime in that case is Lockheed Martin. And then we have Arlington. That's our headquarters. That's where I'm based out of, and that's we have more Navy and aviation programs going on there as well. We do have some boots on the ground out in Huntsville, but we are certainly hoping to grow that and open up an office there, hopefully sometime in the future. I guess the last thing I'd say on this chart is, a lot of us at IDT come from DoD development, so we also have significant tactical and operational experiences that lends itself to the testing of DoD platforms. So moving on to just a little bit of background on automated test and retest, ATRT. The original challenge for us as a company is we were trying to solve, how to get capability to the warfighter faster. And our approach for that was to apply automation to the test and integration world. That's how ATRT was conceived. ATRT is a methodology. It's the process that we go about automating, a test conduct or automating data analysis. And it's also a product suite. And throughout this presentation, I'll go through some of the tools within that product suite. But for this chart here, I really just want to focus on the third bullet: support the efficient characterization of a system's performance envelope. And we did this through using a central model. And the key point there is, in these systems that we're all working on, there's lots of twists and turns throughout these complex systems. There's lots of unique paths of requirements that need to be tested. And in order to conduct that test, we're first modeling that behavior. So that was step one for us. Step two was taking that behavior and then mapping it to requirements, requirements that actually need to be tested to certify the system or to get approval for an actual test event, right? And then thirdly, define verification logic to test those requirements. So we want to bring the verification logic directly into the model to test what those requirements are, or in some cases, it's not requirements. It's actually calculating performance metrics on what the system's doing, right? Statistics. And then finally, fourth, we want to include a data model so that you can link in the specific messages and fields or extraction points directly into the model that are used in those evaluations. So really, that's what we're doing. Soup to nuts is, building behavior, mapping in requirements, making sure the metadata and the verification logic is there for the test, and then mapping in the actual detailed messages and fields that are used in that test. And that's what we're doing for this AADL project. So what's different with ATRT? We're focused on test automation. In some cases, we're looking to automate both test conduct and data analysis. You don't have to do both. Some folks are just interested in the test conduct part. Other folks are interested in the data analysis. Some are interested in using both. But typically for an implemented system, when it comes to a test event, it's not uncommon for that test event to be 2 to 3 weeks. And to just perform the test event, the operators, which can be a large set of folks that are operating the different consoles and submodes necessary to pull these test procedures off, they're at it for 2 to 3 weeks and can take some time. So we have some tools that can actually capture and play back that test automation. So that's on the conduct side. For that test event, say it's a couple weeks, there's typically a large recorded data set that's available. And then this takes even more time and even more folks to actually, manual labor, getting into the data, doing the data forensics of organizing the data in such a way where they can actually test the requirements, right? So what we're doing is at IDT, we're working enterprise solutions that users can log on to a classified web portal, conduct their tests, conduct data analysis, upload results to a central repo, for all of the test sites and SILs to have access to. And that's kind of what we're working on. Technical approach. This chart here is our top level diagram. Not surprising, the model is central in the diagram here. That's AADL. You know, we're for this project we're using OSATE as the modeling tool. That model, that's the architect, that's the design, that's the blueprint. And so for the designer or the architect, the inputs off to the left to that model are, you know, the requirements, metrics, error budgets. These are the things that they'll consider in designing and iterating within that model. Designing a safety critical system directly in AADL. So they'll go through that process, and there's plenty of tools through that process that are already plugins within OSATE that will allow analysis of that system early on in the design phase, right? And so, and within that model, that's where we first, you know, ATRT first appears, right? Within the model, we have this purple icon here, ATRT modeling tool MT. That is a direct plugin to OSATE. It's built into the Eclipse framework. And that navigates through the implemented models in AADL and outputs what we need for some of the other tools in the tool suite here. The green box is ATRT Analysis Manager. The orange box is ATRT Strategy Manager, right? And so the outputs from modeling tool are in the form of database files. So those are all the relationships that tie, you know, all the behaviors and requirements and metrics and verification logic and the actual messages and fields that are used. You know, all of those are relationship files that get, you know, read into our database. And then there's some initial C++ code that actually gets compiled into the tools as well. So those are the outputs. Analysis Manager, the green box here, this is what reads in the recorded data from the implemented aviation system. It, like I described before, it automatically puts the data together, you know, event reconstruction. It stitches the messages together. Typically, those are the messages within a fire control loop, right? From search, track, engage, you know, assess, right? So that can take a lot of time to do manually. We're doing that automatically. And then once the data is, you know, event reconstructed, then we assess it across the requirements and verification that comes from the model, right? So that's Analysis Manager. That's one of the main tools. And then the results from Analysis Manager get fed into Strategy Manager. That's the orange box. Strategy Manager gets all of the relationships from the model as well and overlays those results to those relationships so the test community can see what's passing, what's failing, you know, maybe what they should spend, you know, what their objectives and test requirements coverage should be for the next test event. It also allows you to do trend analysis across test events. So just high level technical approach on this chart. And for the demonstrations, you know, we would go through this full process of, you know, model, how MT plugs in, you know, the outputs from MT, and then ATRT Analysis Manager and ATRT Strategy Manager. The next chart here is just a little bit more information in Analysis Manager. So everything in the green box is Analysis Manager, and we have infrastructure that's used across, you know, for these tools, we have infrastructure, common infrastructure that's used across, you know, all the platforms and communities that we work within. But then there are some, I'll say, more specialized modules that need to be considered, especially for parsing data, right? It's typically different warfighters have different recorded data, different formats, different binary types, and all those kind of things, right? So there are some, I'll say, tailored modulars that we need to consider when building Analysis Manager for a platform. And so what we're doing is we're reading in data, parsing that, getting that to the database, doing event reconstruction, assessing the reconstructed data across, you know, the test article evaluations that come directly from the model. And then to the right here is the actual objective quality evidence reports. Those are tailored reports that get into what the summary of pass and fails are, as well as you know, allowing the user to get down into the data and look exactly at what messages were used in a pass or fail of requirement, right? And then finally, the bottom part of this diagram here is our MBSE track. And the process that I just walked through here, we've implemented this process across many standards and many different tools. We started with Rhapsody, that's SysML. We were also using Magic Draw, that's SysML. We've used UML before, for the standard UML, we've used Rational Software Architect as the tool. And for AADL, and what we're working on right now with Carnegie Mellon is OSATE for AADL. Okay, so the next chart here is just a little bit more on the AADL to ATRT interfaces. We already covered some of this. Again, the modeling tool plugs directly into OSATE. The modeling tool implements a guideline approach that we have to, again, produce what we need, the outputs that we need for Analysis Manager and Test Strategy Manager. The guidelines aren't doing anything outside of the AADL standards, but the model for us in this tool set, it has to be human readable, and it also has to be computer readable, right? So that's what the guideline does. The guideline, basically is the rules of what you need within these system threads within the model to articulate a unique pass-through requirements in the model. And what are all the elements that the tools are looking for, including verification logic, message and field information, etc. So again, we're not mandating anything that isn't already in the standard, but there are a couple of things that you need to consider to build these system threads. And so that's what the guideline is. Modeling tool implements that. As we productize the modeling tool, it will actually, bark at you if something's missing. It'll give you a list of errors of things that are missing to actually complete the system thread. We're working on that to productize modeling tool. And then if everything's compliant and you're within the guidelines, again, everything within the standards of AADL standards, then you get what you need for Analysis Manager and Test Strategy. Moving on for the technical status. This really is a scoreboard of where we are in the SIBR. What I have listed here is the AADL features that we have prototyped and brought in from the model directly and demonstrated within ATRT. We work closely with SEI on this. Again, just to pick on a couple, we've done a ton of end-to-end flows. We've demonstrated modes attached to threads. We've gotten into functional hazard analysis, fault tree analysis, and kind of where we ended up was down into data access and subprograms. So we believe we've covered a big chunk of the standard in working through our initial phase 1 prototype and then the beginnings of our phase 2. And again, the demonstration will showcase these different features and how they're implemented in both the model and ATRT. So the model-based testing, the platform and testbed flows, this is what we're working on right now in phase 2. And in phase 1 and the beginning of phase 2, we were developing the initial technology, what all the interfaces needed to be, what the mapping of our tools to AADL were prototyping, and then also working on scalability from our prototype models into more complex models. So in that, we were working on runtime models that show modes attached to threads and being mapped into ATRT, using simulated data, represented simulated data. We moved into composite modeling, where we were getting into multiple devices, threads, and processors, covering all the views, logical runtime, including execution platform and deployment views. And then some of the properties that we were looking at and evaluating are, bandwidth, latency, power, execution time analysis, things that you would typically, look at in building an aviation system. We were also, as we were working on scalability, we were looking at open source, I'll say bigger models. One that was available through the Joint Common Architecture group, it was the Aircraft Survivability and Situational Awareness model. That one was, available through the community. It encompassed 60 plus end-to-end flows, over 70 requirements, and we were able to plug in and generate what we needed directly for ATRT. And so with that, for the rest of phase 2, we're focused on, what's depicted here in this chart, which is building a UAV system and demonstrating, this full life cycle of using AADL to model the system. And our system is depicted over here on the right in the blue box. It's processors, sensors, the UAV with flight controllers, right? So we're sort of do-it-yourself UAV kit that we're building there. We're using a model to design that system. We're using some of the other tools in the community directly from that model. So we're using Ocarina to actually generate some of the executable code, the tactical code in this case. And then we're using that model again and directly with ATRT to produce what we need, the verification, right? And so for requested demonstrations, this is kind of what we'll walk through. We will be able to open up the model, show you some of the code that's generated automatically from the model, show you the outputs of what ATRT needs from the modeling tool, and then show you loading in the recorded data from what we have implemented for the UAV system, and then showing you the pass and fails and all the OQE that's generated directly from ATRT. So that's kind of what we're focused on now. For the demonstration, again, I kind of covered this on the previous chart. We believe everything that we're doing here fits nicely within the ACVIP vision, right? From requirements in the model to generating the code, deploying and running the code on a target, computer. In our case, it's the hardware for the UAV system, recording that data, and then assessing that data on whether or not the system is compliant regarding the model, right? The model is the model should be the single source of truth for how the system should behave and what the system should be. And then collaboration, again, we're looking to collaborate with other contractors and the government to demonstrate the value of ATRT and this MBSE approach using AADL, or SysML, to understand design issues that your platforms may have or systems, provide assessments of your systems, from a model, and increase the efficiency of the root cause, part of the test and integration cycle, right? I mean, that's the part that takes a lot of time is, finding where an issue is, tracing that to a message and what component is creating the issue. And that's where these tools kind of help. The tools, if you get a failure in the tools, we would show you how to take that failure, map it back to the data, to the actual message that's causing it, and then, helping the root cause process from the start. And then finally, producing hopefully a ton of OQE for your platform and certifications or mission readiness assessments. And then my last chart here, summary. We believe we've demonstrated what the intent of the topic was, automated analysis directly from an AADL model. We're working on end-to-end UAV system to support the demonstrations. We're providing verification support in the model. We're not just doing requirement tracing, right? We're actually using those requirements to certify the system from recorded data as well, right? We believe the tool set and the process supports ACVIP, from the early parts in the left side of the classic engineering, system engineering V chart, through simulating data, maybe using virtualized systems all the way to the right side of the V where you're actually recording data from the implemented systems, whether those are from the SIL labs or maybe those are from, an actual field test event. We've successfully leveraged an infrastructure that we had to date with ATRT and the roots that we had with SysML. And again, shameless plug here, we're part of phase 3, we're looking for partners to exercise these capabilities and grow the tool suite. So that's it for me. And I believe we have a couple minutes of questions. So thank you for everybody's time.
Well, thank you very much, Shawn. That was a great presentation. We just had a couple of questions that came in. The first has to do with the modification required to migrate from SysML to AADL. We understand that ATRT was designed to work with SysML. Was it a lot of effort to migrate to AADL?
Yes, like I said in the presentation, our roots, on the data analysis side were first starting with SysML, the standard SysML we've used a couple different tools there, but the ATRT, the block diagram that I walked through, all that common infrastructure, that software was completely usable as is. So for us in adapting to AEDL, it was really focusing on the front end, right? The plugins to the model. For us, we had a process. We have the back-end ATRT code. So it was just a matter of working our ATRT system thread concepts into a new standard, that's AADL, and into a new modeling tool set, which is OSATE in this case.
Great. Thanks. Now, in the chat, we had a couple of questions. So does ATRT integrate with ELISA, especially its requirement statements associated with model elements, its verification plan and verification methods?
Yes, it does. We read in those ELISA requirements and parse to get the verification methods directly from them. And in fact, some of the composite models and the joint common survivability model that I referenced, we were using that framework in those models as well.
Oh, great. Outstanding. We had another question about instrumentation. So how do you instrument the equipment or the sill to handle bias effects of the measurement?
Good question. That's definitely something that has to be considered. In order to get the data, you obviously have to have a mechanism to record at a very low level, in some cases at the processor level, to get the data to actually test it. Now, the platforms, the warfighter platforms that we've worked with in the past, they have things, war diaries, recording mechanisms built in that have a very low latency, I'll say, as an example, that they can be used in a real test event, and it wouldn't affect everything. But as you're building the system and designing the system, where you would put the probes, and certainly you want to consider what data that you need to get your hands on to actually test some of the requirements, and those latencies, those error budgets need to be considered directly in the model in the beginning, before any of the lines of code are actually implemented for that system under test.
So things like even like cable lengths and things like that, you'd have to represent somehow in that.
You could, if needed. Like I said, I mean, we're working with systems that have data recorders that are within, I'll say, the testing error budgets, but as these new safety critical systems are designed, certainly the probes that you would need to get into, buses and processors, that needs to be considered, for sure.
Okay, well, thank you. And thanks again for a really interesting presentation. I think we're pretty much out of time at this point. So our final presentation of the day, I believe, starts at 2:40, I think. So thank you again, and we appreciate it.